Hello and welcome to this short introductory video series about machine learning. My name is Bojan, and the main goal of my work is to empower more people to take advantage of machine learning by making it more easy to use. In this video series, we try to cover the most important concepts and show how they fit together without going too much into details. If you're a beginner trying to make sense of the field of machine learning, we believe these videos could help you get started. Here's an outline of the topics we'll cover in this video series. Each topic is formulated as one particular question related to the field. In this video, we'll focus on the sixth final question. As a quick recap of the previous video, we've talked about the machine learning workflow and what are some of the major steps. Based on our experience, we define the following 5 steps. Problem definition and data acquisition, which is essential to start our process. Data pre-processing and feature engineering, which makes our data ready to be passed into our models. Selecting and possibly even implementing models that could solve our problem. Training models and configuring their non-trainable hyperparameters through a process called tuning. And finally, measuring the accuracy of our model in order to decide if the model is good enough to solve our task. If it is good, then we're done. And if it's not, then we have to go back to one of the previous steps and continue to iterate until we arrive at a satisfactory solution. As we could see in the previous videos, the field of machine learning and the processes that go into it can be quite complex and overwhelming for many people. This poses a big problem that is preventing machine learning from reaching its potential as a solution to many pressing problems in various areas of our lives. In an effort to hide a bit of this complexity and make it easier for people to use machine learning, new methods started emerging. The overreaching name for many of these methods is automated machine learning, or AutoML. And in this video, we try to answer exactly that question. What is automated machine learning? Before we try to answer that question, let us expand a bit on the motivation for even trying to automate machine learning in the first place. Namely, as we mentioned, the machine learning workflow consists of many steps which are most often performed manually by the data scientist. These steps include selecting models which are applicable to the problem, for each model understanding the available hyperparameters and the valid ranges of values we can assign to them, select values for hyperparameters and assign them, train and evaluate the models, which is often a particularly time-consuming task, and then we need to iterate on this process until we reach some desired quality of our model. The key underlying problem is that this is both painful for the data scientist, and on top of that, a lot of this work is unnecessary. The key observation to be made here is that the machine learning workflow itself is a kind of an optimization problem. We have some search space of possible choices to be made, and we are interested in finding the best model according to some objective metric. In other words, the model parameters are optimized with a learning algorithm. The question is, why can't the same be done with the entire machine learning workflow? We usually start from the obvious, the hyperparameters, but there is no reason not to go even further, at least in theory. The familiar framework of mathematical optimization can be applied here as well. Only 2 issues need to be solved, which are specific to this setting. How do we define the search space, and what kind of optimization method do we apply? First off, let's look at the search space. And let's look at it through an example. Let's say we are given a dataset which contains tabular data. Furthermore, let's say that the problem we are trying to solve is a classification problem. Then what we need to do is to find a subset of all the available models that matches our dataset format and problem type. Let's say that here we come up with 3 model types: logistic regression, XGBoost, which is a type of a boosted decision tree, and the support vector machine. Now, we can expand our search space further, because each of these models has their own set of hyperparameters. Specifically, for logistic regression, let's say we have the learning rate and the weight penalty, among others. While for a boosted decision tree, we will have the maximum depth and some model-specific parameter eta. Finally, for SVM, we have a kernel type and another hyperparameter that is named after a Greek letter. For each hyperparameter, we can expand the search space according to the available values that can be assigned to that hyperparameter. This leaves us with this hierarchical and heterogeneous search space, which is non-trivial. However, at least it's reasonably well defined. What about the optimization algorithm? Before we are ready to examine our choices of algorithms, we need to make two key observations. The first one is that our search space is discontinuous, meaning that it is not a smooth and continuous function like most machine learning models. Furthermore, it's heterogeneous, meaning that its dimensions are highly diverse. The second observation, which is a consequence of the first one, is that the objective function will not be well-behaved. This term, well-behaved, is a mathematical notion that categorizes functions based on certain assumptions we can make about its behavior. And among other things, it influences the possible methods to optimize those functions. Since our function is not very well behaved, we cannot make many assumptions about it, which means that we are better off just assuming it's a black box. In other words, we assume it's a very general function that maps some set into a set of real values. Now, we need to optimize that black box function. Among all the methods to optimize black box functions, there are two most prominent ones: random search and Bayesian optimization. Random search is very simple in the sense that it simply tries out points in the search space randomly. In our case, this means randomly pick a model, randomly assign values to all hyperparameters, randomize all other possible choices, and evaluate the model to compute its score. This process is repeated while keeping track of the best model found so far. And finally, at some point we terminate when we use up our time budget. Bayesian optimization, on the other hand, tries to be a little smarter. The problem with random search is that it doesn't try to take advantage of previous experience. Bayesian optimization tries to fix this flaw by maintaining a probabilistic belief function about the value of all points in the search space, along with the confidence in that belief. It then uses that belief function to make choices about which points in the search space would be the most useful to try, either because they might give us good solutions, or they might improve our confidence about some promising area of the search space. Each time a new score is computed, the belief is updated according to the Bayesian update rule. The process is repeated until we are confident that we are done, or until a time budget is used up. Once we have examined the search space and the optimization methods, we are ready to tie everything together and describe the entire automated machine learning process. We'll look at the steps of this process as they happen through time, and we will look at them from the perspective of the AutoML system and from the user. The very first step that the user needs to take to start the process is to upload a dataset. Once the dataset is uploaded, the system has to analyze it and automatically derive several important pieces of information. The first piece is the decision which feature extraction operators can be applied to the dataset. The second one is which models can we use for the dataset and which hyperparameters do we have to configure. All this information is then fed into a component called the optimizer. This is where the main cycle of our AutoML process starts. What the optimizer does is give suggestions about which candidate of the search space we should sample next. The information about this candidate is called a candidate plan. The candidate plan contains hyperparameter values, among other things. This information is fed into the model which we have selected based on the plan, and we can now train. The output of this step is a trained model. The trained model can be passed to the objective, which is essentially a component that evaluates the model and computes a score. This score is the final metric which we use to determine the value of a candidate plan. This process usually needs to be repeated many times. In theory, it can run indefinitely, as the search space is usually considered to be infinite. This gives us a large collection of plans that ends up being executed, each one having a trained model. In the end, we are interested in finding the model with the best score. The system allows us to then download that model and use it to perform the task we intended it for. This represents the essential automated machine learning process. Developing a system to handle this process is part of what we do at Modulos. We should take note that this process solves only a single certain problem of producing machine learning applications. However, there is often a lot of additional work that needs to be done, like data preparation, cleaning, as well as deployment of trained models, testing them, as well as handling situations where data evolves over time. All these problems represent major challenges of the broader automated machine learning workflow. Solving these problems requires a more substantial toolbox for AutoML, and the development of such a toolbox is one of our major efforts at Modulos. We encourage you to check out our website for more details on all these exciting developments. That's all we have for this video. This was the last video of our series. We hope it managed to clarify some basic concepts and provide an overview of this exciting field. Going forward, we recommend you continue to explore further any area that interests you. We also put some references you might find useful in the description of this video. Finally, feel free to check out our website and learn about our very own effort to make it easier to use machine learning for your specific problem. All of us at Modulos wish you best of luck in your AI journey.